Hello, Royals. For 6.3, let's do some transformations of logarithmic functions. I've just mixed up the bases from the lesson examples, and we'll see what kind of effect that has. So like with all other transformations, we should probably start by identifying which base function is being transformed. So I'm going to say here, I scan through, and there I see my base logarithmic function. So f is going to be y equals log base 1/4 to the exponent x, which is then, or let's say has been, vertically reflected, vertically stretched by a factor of 3. That's from the x-axis. And then shifted right. Shifted right. 2, like that. Going. To sketch the transformations, let's start with a sketch of the original parent. I don't know if I'm going to get the final answer on here as well. Y equals log base 1/4 to the exponent x. We want to be able to do this without thinking about an inverse. The exponent that I place on a base of 1/4 to receive the power 1 is going to be 0. To receive the power 4, I can use the exponent -1. To receive the power 16, I can use the exponent -2. To receive the power 1/4, I can use the exponent 1. To receive the power 1/16, I can use the exponent 2. So it's a decay logarithmic function, something like that. Specific curvature, not really that important. Just like if I was transforming y equals, I don't know, 1/4 to the exponent x, it would probably look an awful lot like y equals 1/3 to the exponent x. Okay, here, let's label that our original h, just with a letter so we can label it. Okay, this curve is vertically reflected. Now, when vertically reflected, decay logarithmic curve is going to look like a growth logarithmic curve. Make sure we understand the reflection is happening across the x-axis, so the point on the x-axis is going to be invariant. Vertical stretch by 3 is happening from the x-axis as well. So again, the point on the x-axis is going to be invariant. This normally with vertical stretches, we don't have a lot of parents that cross the x-axis. I guess the sinusoidal functions would be the exception. So when we stretched our sinusoidal functions, that moved their amplitude away from the x-axis, but didn't move the point on the x-axis. The same thing's happening here. We need to get used to not drawing a curve that is taller. And this is why effective teachers have asked you not to think of vertical stretches as being taller. It's faster. Notice that my curve is below the original, but above the original, depending on what side of the x-axis I'm on. Okay, I am steeper. This curve is 3 times steeper than what it used to be. And then we shift it right to, well, yeah, this is getting a little bit crowded, so why don't I just get a little bit of space here for my new curve? Instead of thinking about every single point shifted right to, maybe we can shift our asymptote right to. So now we have a new vertical asymptote of x equals 2. I think we can track our x-intercept in this case. It was 1 originally. After the reflection, it was 1. After the stretch, it was 1. After the shift right 2, and now it's going to be 3. But maybe we don't care that much about it. Or maybe we'll discover a more efficient way of finding it in the future. This curve isn't that interesting over here. It's quite steep, so you're not seeing it go off in that direction. It should eventually. Here's f. The y-intercept, f of 0, is not going to exist. Notice if I try evaluating f of 0, I would be asking what exponent do I put on a base of 1/4 to receive the power -2, and I cannot get a negative power from a positive base. Doesn't matter what exponent I use. Okay. Domain and range are visible from here. End behaviors are visible from here. Let's... I guess we'll try those for this original. I'm not sure if we'll fit it in for the new one. So for f, we have a vertical asymptote at x equals 2. We have a domain where x is every real number that is greater than 2. We have an unrestricted range. End behaviors, best seen from the sketch. Looks like as x grows without bound, y grows without bound. And if we want to talk about rates of change, our rates of change grow without bound. approach 0 from values that are greater than 0. As x decreases, as x approaches 2 from values that are greater than 2, my y values decrease without bound, and my rates of change increase without bound. Sorry, I just got a message that my children just arrived home, so we might be interrupted soon. But let's see if we can get through this example pretty quick. All right, maybe we factor first before we write our base exponential function. Log base 2, -1/4 x minus. Check with distribution. -1/4 times what gives me -1. It's going to be +4. All right, -1/4 times +4 is -1. -3, you can do -1 divided by -1/4 like that, and then multiply by the reciprocal. And you'll get +4 there. Our base function here is y equals log base 2 of x. Let's just do a real quick sketch of y equals log base 2 of x. I didn't think of generating a table of values. I just saw a growth curve like that. It is going through 1, 0, 2, 1, 4, 2, 1/2, -1, like that. It is horizontally reflected. So it's some sort of weird decay curve, but just like behaving in a totally different way, right? X-intercept is now -1. We can try tracking the x-intercept here when we look at this horizontal stretch by 4. That horizontal stretch is from the y-axis. So now my new x-intercept is -4. And then I shift left 4. And now my new x-intercept is -8. If we're getting stressed out about tracking this x-intercept, don't worry about it because we're about to lose it when we shift this curve down 3. And just like horizontal shifts on exponential curves are kind of hard to see, vertical shifts on logarithmic curves are kind of hard to see. Take this curve and shift it down 3. Well, it's going to look pretty much the same. Okay. Key features that I'd be looking for are the new asymptote. Not sure what I'm doing here. Let's go like this. So there's my y-axis. The logarithmic curve with a vertical asymptote of x equals 0 has been shifted left 4 in factored form. So let's draw that in. X equals -4. It was a growth curve that went up to the right. Now because of the horizontal reflection, I guess it's going up to the left. You could say it like that. So I'm just looking for something that kind of goes off in that direction. The directions of the question didn't ask us to label any intercepts. Once again, we don't have a y-intercept. There will be an x-intercept. It's going to be an irrational number here, I'm pretty sure. We'll need to figure out how to solve logarithmic equations to find it, but maybe we don't care too much about it for right now. Okay, we should be able to state the domain and range, state our end behaviors, state our behaviors of the rates of change from this sketch. Okay, no inverting, no tables of values, no mapping statements, no grids either. Just good old-fashioned sketches. Okay. You get better at transformations and sketches by practicing it, so try it out.